abstract or generate a hierarchy like the one I'm showing here. So, so there are two components here. One is there is a recognition problem, or it's called plan recognition, where we want to learn the objective of the agent at different stages. And one is the strategy. We're learning strategies because, you know, in this example, I went to the airport, but perhaps I could just take the train. That would be a different form of getting to NSF, or perhaps I could just drive the car all the way to Washington, D.C. It's only 3.5 hours from where I am. So these strategies could be stored and could be reused when solving this problem. And it doesn't have to be the exact same problem, right? So maybe I'm not going to NSF, but I'm going to another location in Washington, D.C. Then most of these hierarchy could be reused for that purpose. So let me fix the terminology that I will be using, and this is as much for you as for me to make sure that I would use it. The inputs are actions. In the terminology of HTN planning, we call them primitive tasks. So primitive tasks, we say, is accomplished by an action. And then we have these compound tasks, which are tasks that are decomposing through other tasks. These compound tasks can be decomposed into other compound tasks or into primitive tasks. So that is terminology, primitive tasks and compound tasks. We have a task decomposition. That is, we are getting a compound task and decomposing into simpler tasks. That is called a task decomposition. So briefly, hierarchical task network planning, or HTN planning, is the problem of we're given a collection of tasks that we want to accomplish, and these tasks are decomposed into simpler tasks. So we are taking the compound task and decomposing into primitive tasks, into simpler tasks, and we continue that process recursively until we reach primitive tasks, at which time we apply operators, which are generalizations of actions. So there are two kinds of knowledge artifacts used in HTN planning. One is the operators, same as the strips planning, says as other forms of planning. I'm pretty sure you have here a PDDL, which is a language for expressing these operators. And they are these other knowledge artifacts called methods. And those are the ones indicating how and when to decompose a task into subtasks. So those are the knowledge artifacts. The methods are the knowledge artifacts containing the task decompositions. So here is an example of a method. A method indicates how to decompose a task and when to decompose it. How is, I'm driving to the airport, and there are three variables here, P, C, and A, and there are two subtasks, and that's the how, which is I have to take a local road, and then take the highway, and I'll get to the airport. In the when are the applicability conditions. So this parameter P is a person. There is an airport A, there is a car C, that's the one I'm using, and so forth. So those are applicability conditions. So this is the knowledge artifact that we would like to learn. In HTN planning, as I mentioned before, you also need operators. So they accomplish primitive tasks. So the drive task is a primitive task because it's accomplished by this operator. And operators have the usual components. So let's talk about why there has been a recurring interest of HTN planning over the years. So this is an ongoing topic. One of the reasons is expressiveness. So Kuglam, Errol, Indina now, and others have shown formally that HTN planning is strictly more expressive than classical representation. So using methods and operators, you can express knowledge that cannot be expressed in operators only. So here is a simple example of that. This is a top-down view of a game called Unreal Tournament. And this is a mini game in Unreal Tournament called Capture the Flag. No, not Capture the Flag, Domination Games. There are these 3 locations. And there are 2 teams competing to control those locations. So there are 2 blue and red, 2 teams, blue and red. And whenever blue gets to this location, then this flag will turn blue. Every 3 seconds that the flag is blue, blue team gets 1 point. And they're basically competing to controlling these locations. And here is a very simple strategy. Perhaps I would like one of the players to go back and forth an arbitrary number of times between these locations. Very simple one. I can very simply write a simple method that does that. But it's not possible to write an operator that does that an arbitrary number of times. Again, a fixed amount of times, of course, we can, but arbitrary is not possible. Whereas with methods is simple. And there are other more complex examples, but this is just an illustration. HTN Planning has this expressiveness, and we are that's one of the reasons why there has been a recurrent interest in HTN Planning and for some of us learning these HTNs. The second one is interest in HTN Planning is applications. So there has been a number of applications over the years. Part of it is that it's natural in many domains to this hierarchical representation. So in military domains, is natural to represent the plans, and in fact, many of these military units are represented hierarchically. So this hierarchical representation is natural. They have been used for UAV control, for digital games, for robotics, and others. So there have been a number of applications for doing that for HTN Planning. And this is one, again, we did years back where we took a particular kind of operations where they're going to basically rescue. There is a disaster like a tornado or tsunami or something like that, and they want to rescue people who are in that catastrophe zone. In this kind of task is really naturally modeled in a hierarchical form. So there are many domains that are amenable to these kinds of hierarchical decompositions. That's a second reason. And related to that is we now here perhaps some of you are working in this very important problem of explainable AI, right? We want to see not only why did the algorithm generate a plan, we want to understand why, how did it came to that plan. And having a hierarchical decomposition provides a natural way to explain how that plan and why that plan was generated. This motivation of HTN Planning predates what is called explainable AI. Researchers like Edwina Riesland and others have, Katia Sikara and others have made this point over the years, that this hierarchical decomposition can be seen to what we call now explainable AI. The third reason is efficiency. So because these planning domains include the methods can be seen as a sketch of a solution. That's one way to see methods. And therefore, you can write highly sophisticated methods if you're handcrafted them that take into account efficiency or things like time constraints or cost. A variety of things can be done when you write these methods. Of course, the problem here, we like to learn those automatically. But the recurrent interest in HTN Planning is because it has shown efficiency over a number of domains over the years. Now, I don't want to walk from this presentation saying, oh, I'm going to, HTN Planning will solve every problem, and that's simply not true. The big caveat for the successes that I mentioned in this motivation is that you have a very robust HTN representation. You have high quality methods that will allow to perform this decomposition. And for that, you know, that will influence the problem substantially. In fact, from a complexity standpoint, HTN planning is from a different complexity class than standard street planning. And the flip side of that, of course, is that it is more difficult to solve. Meaning, if you have methods, for example, that are wrong or not carefully crafted, you may get terrible performance results. So you need good HTN knowledge in order to have these good results that I've been mentioning. And there are domains that are not naturally impossible, but at least I would say not naturally modelable, amenable for HTN representations, right? So if you think about the problem of checking whether a number is prime, basically what you have to do is, you know, go from 1 to the, or from 2 to the n divided by 2 number, and one by one checking whether any of those numbers is really divisible, or whether n is divisible by any of those numbers. So it's a iterative process, and there seems to be no workaround. There's really no structure there that I know of. Another one is there are domains that are puzzle-like. So I'm pretty sure all of you have heard of Bloxworth, and there are algorithms that are good to solve Bloxworth, but it's not a domain that really is amenable to these kind of hierarchies. They are not evident. I know some of you might have used the HTN planner called CHOP or CHOP2, and you know that there is, if you have used it, there is a very high quality methods there to solve Bloxworth. But when you look at the methods, they're really more like a programming. They have these strategies that are well known from a paper from Dana some years back. It's not really a naturally hierarchical domain like the ones I mentioned, like in military or some of the game strategies. So that's a caveat here, that not all domains are amenable to these kind of representations. And that means if we are trying to learn this automatically, you know, from the traces trying to learn, what we're trying to do when we're learning HTN is learn the structure. And then if it doesn't have a hierarchical structure, probably those algorithms that are trying to learn these hierarchical methods will perform well. Okay, so let me try to run a little bit how the HTN learning problem can be defined in a few variants that have been explored by researchers over the years. So the first one is, there is usually a need for background knowledge. The reason is, I mentioned the tasks, and there is a task like here, travel, this person is going to location L. That's a task. But the tasks in HTN planning do not have semantics. And what I mean by that is, if you think about a planning problem, when I have a goal, the semantics of the goals are very clear. Typically, it's a statement on a fact that is true in a state. And there are operators or actions that when you apply it, add new facts to the state. And therefore, I can construct a plan that will add that fact, that goal that we're trying to reach. And then I know that my plan achieved that goal. And of course, I check that every one of the preconditions were applicable in the state. So there is a very clear semantics of what the goal is. But for the task, you don't have something like that. Basically, the formal notion of task is, the task is defined by whatever the methods decomposing that task says the task is. This is very informal, but that's what it is, right? So if we have a task called travel, I say travel, and you and I, as humans, have an idea what travel means. But I have called my task foo, and with this parameter, we have no idea what the task is. The system has no idea. The only way we'll know what the task is examine the methods and seeing how those methods decompose that task. And that will give an idea of what the syntax or what the semantics is for that task. So as a result of that, that's a big problem for learning, because we are trying to learn these hierarchical decompositions, and the tasks really have no meaning. We are trying to learn in an inverted problem, right? I'm telling you that if you give me a domain, the only way I can tell what are the tasks, what are the meaning of those tasks is by examining the methods, so I can tell how those tasks get decomposed and start getting an idea of what those tasks means. But here we are trying to learn the methods. So then if I give you a collection of names like a collection of tasks, then I would not know what to do with them. So as a result, researchers have suggested a number of alternatives for the purposes of the learning problem. So these researchers from Georgia Tech, Murdoch and Gold, Ashok and Beal, they propose what they call an annotated task. And the idea is, yes, you have the task, but you explain what are the semantics of the task by indicating what are the preconditions and what are the effects associated with every task. And many researchers, including myself, has adopted this as an additional input for the learning problem. We are requiring that they give us the traces, but they also give us the annotated tasks, which tell us for every task, what are the semantics in terms of these preconditions and these effects. So that's one way that some background knowledge is given of the method of tasks. Other researchers have suggested the use of horn clauses, Pat Langley and Nuka Shu, and others have suggested this is a representation of a horn clause. It has some effects and some conditions under which those effects those conditions are made true. But it's a way to define, ultimately it's a way to define this task knowledge, and it's a way to provide additional knowledge, otherwise we will not be able to learn the methods. So here is one way to define the planning problem. We're going to, in terms of input outputs, they give us a collection of plans, which is a sequence of actions. And I should have mentioned they probably are annotated. So you have the initial state, the final state, perhaps you have the intermediate states. Well, if you have the initial state and that's all you need, because if the actions are given, the operators are given, then you can compute all of the intermediate states. So you're given a collection of plans, the collection of operators, the initial states, so you can propagate what are these intermediate states, and the annotated tasks. So those are the inputs. And what we're trying to learn are the methods. So that is, what are the task decompositions and what are the applicability conditions, the preconditions of those methods. And obviously the tasks will be given, are annotated based on these tasks that are given as input. So that's one variant of the learning problem. Researchers have explored different variants over the years. Another one is one where, yeah, some constraints are added. So, for example, there's some work where we're trying to learn the actions in addition to the methods, and you're not giving a complete state. You're giving, it's assumed that you're in a partially observable environment, and therefore these traces are annotated with partially observed state conditions, not the full state. Other works have tried to learn, assuming that they are working in a non-deterministic domain. These operators are non-deterministic, and therefore you're trying to learn methods, but now working for non-deterministic domains. Others have to, I mentioned others have to try to learn. Now you're giving the plans, this background knowledge, but you're learning not only the methods, but the operators. Others say, okay, I'm going to give you the plans, I'm going to do the collection of operators, but I'm not going to give you the annotated tasks, the background knowledge. I'm trying to learn what are the tasks. And to do that, they basically define the tasks as what are the goals that are being achieved by the traces. So there are different variants that have been explored over the years. Now let me discuss some related problems to the problem of learning HTNs. And again, I'm trying to give you more context here before we dive into the actual methods. I think the context is important. There has been a lot of work over the years on learning the operators. So Chong Yang and multiple other researchers. So that means you're learning you're doing perhaps as input the skeleton of the action, but you are learning the preconditions and the effects, including the delete and add list. So that's one related problem. Again, in HTN planning, there are some variants that learn the operator, but they also learn the methods. So the big difference is in HTN learning, we may be trying to learn the operators, but we also are trying to learn the methods, or we are not learning the operators, we assume those are given, and we are trying to learn the methods. So that's one difference. The one is macro operator learning. And just with this schematic, I can try to illustrate the work, and you can look at Adi Botea's work on this, and many others have worked on this problem. A macro operator basically allows you to jump 2 or 3 states or more states. In this case, we have a macro operator that performs this one of these transportation domains, and is performing 2 operations at the same time. Is performing an unload and the drop. But there is defined with a single operator called unload drop, which will have the preconditions. For example, in this case, the package is in the truck. And the effect would be what happened at the end, which is the package will be in this platform and is no longer in the truck. So it's basically computing the effect, compounding the effects of these 2 actions. So the macro operator does not the same as HTN learning, because in HTN learning, we are precisely interested in these intermediate actions. In the macro operator learning, you will not know. You will only know what are the, what was the state before and what is the state after. But nevertheless, it's a related problem because you basically have to subsume multiple actions into one. Again, but the big difference is that in this macro operator learning, they don't keep track of what we call the task decomposition, how are these things being grouped. Another related problem is the learning grammars, and this has been a recurrent problem, very old problem actually. Many people have worked on this problem for many, many years. This is an example of a particular kind of grammar called a context-free grammar that allows you to transform variable and is used to generate strings, as they call it in that terminology. And then you're trying to learn these grammars. And these grammars in some way mimic hierarchical structure, because you could say, oh, this is a task, and I replace this task with this other task. And this task, I can decompose it into when it's a character, we could look at that as a primitive task, and it's a variable we could say is a compound task. So it has a flavor of learning HTNs. The big difference versus learning HTNs is that they would not learn the applicability conditions, right? So here we could use, and researchers, I know Rao Kamapati a few years back, he used methods of learning grammars to learn the hierarchical structure of a domain. So those things can be used. But the part that they will not is not done here is learning the preconditions, or the applicability conditions. Another related problem is plan recognition, and the way I introduced the talk initially is kind of a plan recognition, which is basically trying to devise the intent of a plan. The difference versus, so they have many common characteristics, and plan recognition frequently involve HTN representations. It's a natural way to infer intent. The difference is in HTN learning, we're trying to learn those methods in order to reuse them. Whereas here, they're trying to just, you're given one plan and trying to understand what that plan is doing, and not necessarily for planning again in other problems. Okay, so with that, I mentioned there are 2 components of the learning problem of methods. One is learning applicability conditions, and the other learning structure. I'm learning in separate. I'm presenting them in this presentation separately: learning preconditions and learning the structure. Many of these systems that I know of actually learn both at the same time. So basically what I did is take the component where the preconditions separately here for the purposes of this presentation, and the one structure presented later. But many of these systems will learn both of them. So there's a variety of methods that have been explored over the years. And here I'm showing only just 3 of those. And again, there are many more methods. People have studied inductive logic programming. So there are frequently some kind of ontology of objects, and they try to learn these methods that way. And it's very effective in a situation where we might not have the actions, and we're trying to learn the actions. And the drawback is might yield incorrect generalizations. But it's very robust. So even if I have some noise in the training data, it will still learn something that mostly right. There has been trying to use version spaces. That's a learning method, and it has a beautiful property that you always will learn correct generalizations. But it requires not only positive examples but negative examples. So you will say something like, in this situation, I should not apply this method to decompose this task. So I have to give negative examples. In some situations that might not be possible. The other thing is very brittle. If you have any examples that are, you have examples that include, that are mislabeled. So if something was a positive example, then you meant to say negative example, then you will need, it will collapse the version space. Somebody asked if ILP require negative example. Yes, it may require, but not necessarily. So in fact, I'm going to show you one method here that doesn't use negative examples. Another one is constraint satisfaction. In particular, people are using things like MaxSat. It has perhaps less knowledge requirement in terms of we don't require negative examples, we don't require an ontology. But on the other hand, it doesn't necessarily converge because you're trying to find the maximum collection of conditions that are satisfied. And you need a lot of examples. So they have the drawbacks and presentation. Let me give you a few examples, and I'll have to control my time so I can move to other parts of the presentation. So this is an example of ILP. So in this situation, we are seeing, and again, we are only learning here the applicability conditions. So we are giving particular situations where we have a task, it has been decomposed, the decomposition is given. When we are trying to learn the applicability conditions, and we're giving an example of a situation or a concrete state where that task happens. So we may learn the applicability conditions. And of course, what we would like to do is generalize, right? So convert this as a concrete city, a concrete truck, a concrete package, and we like to generalize it, convert them into variables. So the problem is we have the concrete decomposition we want to generalize. So we want this method that will have a generic decomposition. But when you generalize, you lose information. And then there's the danger that when you apply the method with a different instantiation from the original that you got, you may yield an incorrect plan. So then there are some additional information that typically is provided, for example, an ontology. So here we are saying that there are two kinds of vehicles. There are vehicles, and a tanker is a vehicle. So you have this kind of ontology. And with that information, then one will be able to discern or compare methods. So we have one method here that is saying we are having a tanker that requires a liquid, and we have another one that is actually a refrigerated tanker, and liquid is perishable, like milk. And this is refrigerated, meaning one of these tankers that have like some kind of AC unit to cool things down. And then with this kind of information, then one will be able to compared it to, and for example, using the ontology, know that this is more general conditions and this is more concrete conditions. Still variables, but these are more concrete conditions. And for example, put preferences on the ones that are more concrete. This illustration is a situation that if you use the more general method, then in a particular situation, then perhaps it will not work because it will generate a plan that is incorrect. And it's most likely that you will be able to generate a correct plan if you use the more concrete one. That's all I want to say about this. And again, there are references at the end on the concrete methods that were used, procedures that were used. Let's talk about version spaces. This is a concept learning algorithm where you're giving a group of instances. And I mentioned there has to be some negative conditions. So you're giving here a target. We want to learn the subject. There are three parameters: the size, the color, and the shape. We are giving some positive instance of the concept, some negative instance of the concept. And these version spaces start with two extremes: the most general condition and the most concrete one. And then using these positive and negative examples, they start refining the conditions. So I don't want to get into details of the procedure, but basically you start replacing some of the conditions here with variables that are consistent with the positive examples and inconsistent with the negative ones. And if there are sufficiently large number of conditions, positive and negative conditions, and there is no noise in the training data, then these version spaces will converge to a concept that is the one that satisfies all of the conditions. Again, making very powerful assumptions in terms of what kinds of, how many positive examples, how many negative examples you have, and bias in the representation. The way that has been used is they include for these version spaces. They will say, okay, I'm going to include a bias in my representation. I'm going to assume that there will be at most 3 preconditions in my method, and then I will include generalization rules. Like typically, for example, I replace a constant with a variable. Then that's a generalization, or vice versa, an instantiation will go the other way. Negation is simulated that saying, okay, if it's anything other than D, that's a representation for a parameter. That's a representation of the condition. And then you give enough examples, and then you learn your conditions. Yeah, I don't want to get more space. You can do that Oktay's paper on that topic. One condition, we use this in a, we had a project a few years back, and we use these kind of algorithms. In version spaces are fantastic, but they do have the issue that they are brittle. So there were examples. There was a game environment, so we are acquiring the knowledge from the games, and then there were some situations that were incorrectly interpreted by the program, and then example were mislabeled, and then the result of that is basically it will collapse this version space, and nothing was learned. So they have the drawback. This is another work, in the idea of using constraint satisfaction. The idea is the following: here are your plan traces that you receive as input, and one can process those traces automatically and extract constraints from those traces. Then using something like MaxSat to solve the constraints, and based on the constraints that are solved, learn the method's preconditions. And in this work, it was also done not only the method, but the operators. So let me give you an example of what I mean by that, how we extract conditions, extract constraints, and how we solve them. So, so again, we are assuming this task decomposition is given. So this is the example that is given. And in this work, we are trying to learn both the actions and the methods. And specifically the actions, meaning the precondition effects, and the methods preconditions. So suppose we observe a condition alpha, an atom in a state. So this is the plan. These are the methods in this order. And we observe this condition alpha that occurs in this state. Then what we can process, process this trace and add the following constraints. One is we'll say that alpha is a precondition of T6 because alpha happens before T6, the action T6 is applied. Alpha is a precondition for M6. You see, this is the method M6. If the method was applied, it was applied in this state. This was one of the conditions in the state. So we're going to have assume as precondition that alpha is a precondition of M6. Alpha occurs after T5. So we're going to add an effect indicating alpha is an effect of T5 and so forth. And then each constraint will be weighted based on the number of occurrences. So if in all of the traces, like we have 300 traces, and there are 20 occurrences of alpha occurring in the state right before T6 is applied, then we will have this constraint with a weight of 20. On the other hand, suppose we have this method 6, and this alpha only happens once, then this condition will have a weight of only 1. So that's the way we construct these conditions. Then these are given to a maxat solver, which takes into account those weights, and will try to find the maximum number of clauses. In this case, each of these constraints is a clause. The number of clauses that will be satisfied, and will make some of those true. So for example, it may make this condition that alpha is a precondition of M6, that clause will be made true, and therefore we will add as a precondition of M6 the condition that alpha as a precondition. So that's a procedure, and that's one way to learn this. And again, it has the good thing is doesn't require labeling of negative examples or background knowledge. The negative part is that it's using maxat, so it's not a probable correct for all of the examples, and therefore it may make some mistakes in terms of learning precondition. There's a question here: doesn't maxat approach resolve the brittleness issue of version space when there is no constraints with infinite weight? Let me see let me read the question again because I'm having an issue. Does maxat approach resolve the brittleness issue with version space? It does. The first part of the question, yes. It resolves the brittleness issue because if I mislabel, I see. The answer is yes. Pashot, and the answer to your question is yes. This is the brittleness issue because suppose that I mistakenly label some of the atoms here have been mistakenly labeled, like alpha didn't happen, and I labeled a few times. Because this is taking into account the weight, then those kind of mistakes will be negligible. You have multiple examples, and therefore it will not learn from those. So yes, it really solves that issue, and that's one of the high points of using constraint satisfaction for solving this problem. In the paper, look for author Chong Yang, and look for a paper. It's listed there. There's a system called ARMS, learns actions using the same procedure. And you're going to see that what they do is they purposely give noise as input. They purposely include with some probability, some of the atoms there should be an atom alpha with some probability they are removed, or with some probability new atoms are added that should not be there. Very low probability, but still, with very low probability, that doesn't really affect the learning. So yes, they are more robust in that sense. Good. With that, let me move to learning hierarchical structure. I'm going to talk about two alternatives, and again, these are complementary to the part of they complement the learning preconditions because I just, for the sake of the presentation, I separate them, but actually there we did the same procedure. There are at least two kinds of alternatives. Those that are incremental, so you trace by trace are learning the methods, and others that are consolidated, where you take multiple traces at the same time and do some statistical analysis and others on the traces to learn the hierarchy. So both of them have been explored. So let me start with the incremental one. Again, incremental means we are learning one by one, methods, a subset of methods, and we increase them. They all have or most of them have the same basic step. Again, suppose that we give the annotated task. So we know the task, but we know these preconditions and effects. So we have that as input, and they give us a trace. So I'm representing a trace with these. So each of these squares is an action, and this is simply the order that they are executed. And then what we do is they will identify. For example, and I mentioned this. This is not just the actions. We also give the intermediate states. And in this case, we observe that the preconditions, for example, are valid in this state before this action is applied, and the effects of the task are valid in this state after this task is applied. So therefore, we will say that this sequence of actions, this subsequence of actions, will accomplish this task. And obviously, you may have different parts, different the trace where these preconditions and effects are satisfied, and you may have multiple tasks, so you have that kind of overlapping there. But for now, the basic step is you're going to annotate tasks, the preconditions and effects, you're going to trace, annotated with intermediate states, and then you will identify using the preconditions a state where the preconditions are valid and a state where the effects are valid, and then one will say, okay, this subtrace here accomplishes that task. The second part is, how do we learn hierarchical structure? Well, so I have a task T prime that, for example, accomplishes this trace, and I have a task T, again, because of the annotated task precondition effects, that accomplish the subtrace of this trace here. So in that case, I will say that this task T prime can be decomposed into this primitive task, this action, and this subtask T. So the task T will appear as a subtask of T prime in the method decomposing this task. So I can start constructing a structure that way. Not only that, but I can learn recursive methods. How do I learn recursive methods? Remember, these tasks are preconditions and effects. So I may have the precondition and effect for this task being completed with this trace, but also completed with this subtrace, in which case I'm having a recursive method. So recursion is able to learn recursion in those cases. Obviously, I'm pretty sure you will see that opens a number of issues, because what happens if I have multiple ways to decompose the task in a trace? How would you choose? You may have multiple also decompositions. So how would you choose a structure? Would you use left recursive, right recursive, or order? How would you do that? So here is one system, HTN Maker. HTN Maker decided the authors of HTN Maker decided we're going to enforce right recursive. So we have, for example, this is an example of a task. It's a delivered task, and it has no preconditions, and the effect is the package is at location L. This is the transportation domain. So the delivered task basically is a goal, which is the package is at the location. And then when you look at a trace like this, we have, again, transportation domain. We are unloading a truck, loading the truck, fly airplane, unload airplane. At every point of time, you're basically accomplishing this deliver task. Therefore, you could have many possible decompositions. The way HTN Maker solved that problem is saying always the task will be decomposed into two subtasks. The first one is primitive. In this case, it will say unload. And the second one will be the recursive task, which is deliver. So the task will say, we have one method that says deliver this package to this location, first do the unload, and recursively call deliver. So now you're in the situation, you're deliver task, now load and deliver. Now just in this one, the deliver is fly and deliver. And at the end, there will be a method with a single subtask where the deliver will be composed by the unload plane. Some of you may be thinking, but what happened with infinite loops, right? Because this is right recursive. You may have an infinite loop. And the issue here will be the applicability conditions, right? So what we talk in the first part of this presentation is if the learning procedure for the preconditions is careful enough, then it will apply this this method to deliver the task only when the package is in the truck and the truck is at that location. And once it applies the method and it will load the package, then this method will no longer be applicable because the package will be in the location. It's no longer in the truck, and therefore this other method will be applicable. So that's the way the system HTN Maker uses that. Here is another one. There is I mentioned uses of HTN planning in hierarchical planning. One area of AI research that hierarchical plan decomposition is used very frequently is an area of research called cognitive architectures. And that's a different topic altogether, but you can Google it. There are SOAR, ACTAR, ICARUS, many others, and most of, I don't want to say most, but many of those use these hierarchical representations. So this is one of those. In ICARUS, it's a cognitive architecture, so it's using long-term short memory and all of these things that they model. But there is this component where they're trying to learn a hierarchical task network. And this is how they do it. So they have an HTN planner, and they have a planning problem, starting a task and starting a state. And they have some ways to do what is called goal means analysis. So they actually can plan forwards and plan backwards using a particular variant of HTN planning. But the point is this: suppose that they're using their planning, they're using the means and analysis, and they're generating a plan forwards and generating a plan backwards, and they come stuck. Stuck meaning they move forwards and they reach this state, and there is no other way to move forward from that state. And they're doing backwards chaining, and they reach this state, and there is no other way to continue backwards. So they will have this gap, as they call them, in knowledge. Based on the HTN method that they have learned, they don't know how to get from this state to this state when a particular task is given. And therefore, what they do is they will use standard planning to generate a plan filling this gap. And then they will learn the methods from that plan to fill this gap. This is this kind of learning is something called telereactive learning, and this is for logic procedures, people have used that a lot, and ICARUS uses telereactive, but it's the telereactive learning. But the idea is they will only try to learn when it's needed. So when they find gaps in the knowledge, they will fill those gaps and learn new methods and therefore continue. So that's another procedure. So that's another example. Just a moment, I think. The consolidated is the one where here we go one by one, right? Now the consolidated, we are looking at many input traces at the same time. I mentioned the MaxSat solver, so for serving the preconditions, that actually was companies also use MaxSat also to learn the task decompositions. Very briefly, I don't have a slide for that, but very briefly, that the way that works is they will have a potential task decomposition and it will construct a constraint. It will say, can task T decompose into T1, T2? It will add as a constraint. And again, if it happens multiple times, it will be weighted and it will be part of the MaxSat process. And those that will become true, those will become methods. Let me turn about this other one, which is learning hierarchical goal networks. And again, it's consolidated. Very briefly, I don't want to spend too much time on this, but there are multiple variants of hierarchical knowledge. The hierarchical task network, every echelon in the hierarchy is a task, a compound task, and only on the leaves is a primitive task that's completed by the actions. The hierarchical goal networks at every echelon in the task, or in the hierarchy, there is a goal. So it's always accomplishing one goal in the hierarchy. Like for example, here we want the location of submarine to be detected, and it has these sub goals. So it's the hierarchy has every element in the hierarchy is a goal. It has been very well defined. You can look at because Shivaskava PhD dissertation, he defined very carefully what these hierarchical goal networks are. And for example, it shows that the expressiveness of hierarchical goal networks is equivalent to total order HTN planning. The reason I'm mentioning that here is that there has been some works where they're trying to learn these HDNs, these goal networks, that now they don't assume the annotated has to be given because now we have the goals and therefore one could learn the goals hierarchies. This is the way they do it. This is again an example. So now we have all of the traces at the same time that are given as input. And this is again, each of these is an action and annotated with intermediate states. And what they do is they represent this problem of learning this hierarchical decomposition on the goals. It represents what they want to do is learn the structures. They want to learn sub-goals that frequently happen in these traces. And what they do is they will cast this problem as a word embedding problem. So they will see these traces as text. Each of these individual traces is a sentence. Each of the applicability conditions or in the state are words, and each of the action is one word. And then they give it to a word embedding tool like word to vector. The way these word embeddings work, in particular word to vector works, is they will look at the context in which a word appears. And the translation for this context, if it will look, for example, if a particular condition frequently happens before a particular effect. And it will learn this is showing a three-dimensional. In fact, this is multi-dimensional vector. I just showing the three vector dimension just to illustrate them purposes. But it would be a vector representation for each of these planning elements. And it will have, this vector will have an orientation in such a way that when elements in the plan frequently occur, like for example, a particular applicability condition happen frequently near some action, then those vectors will have similar orientation. So in this example, this is an example, this is an illustration of that. It's not a real example again, because this is in a hyperdimensional space. It will, for example, detect that the condition of the airplane is closely, has very similar orientation to the airport. And that's because in this transportation domain on which it was tested, airplanes require airports to land into the part. So that's why they will have a similar orientation. And then it will do clustering algorithms to identify similar conditions. And that's how it will start. And again, the purpose here is to identify a hierarchy among the goals So let me just show you an example. Let me skip this part. Let me show you an example of how this works conceptually. What you see here is a map of Manhattan, the part of New York City. And you see on this other side is New York City. Excuse me, Jersey City. Jersey City. So here is Manhattan, here is Jersey City. Those of us who had been there, we know that if you are in some location in Jersey City, basically you have two ways to go to Manhattan. Either you take the Holland Tunnel or you take the Lincoln Tunnel. Okay, you can take a ferry too, but I mean with your car. But most people will do either of these two if they're in this area. You may have heard about planning landmarks. So suppose for a moment that Lincoln Tunnel is in repairs, then all of the traffic going from any location in Jersey City to New York will have to go through the Holland Tunnel, and that will become a landmark. Now let's open the Lincoln Tunnel again. Now this is not necessarily a landmark because it may go here, but it will be kind of like a partial landmark. And what will happen is when we run this word to vector and start putting this representation together, these kind of landmarks will have a very high. They will have a very high value in a score that we compute. This score is computed. You run a clustering algorithm. You will have all of these, in this example, all these locations in Jersey City grouped together because they co-occur very frequently. All of these locations in Manhattan near Holland Tunnel also grouped together because they occur frequently. So you have these two clusters. The Holland Tunnel will belong to either one. And then we ask, what is the atom, or we compute, what is the atom in one state that is the closest, in one cluster that is the closest to all of the atoms in the other cluster, and vice versa. And what we will do is we will find the Holland Tunnel, it will find the Holland Tunnel, or it will find the Lincoln Tunnel in this example. So, and you can continue recursively for each of these clusters, zoom in, do something like aggregate cluster algorithms, and then you will continue finding new sub-goals within those, and now you have a hierarchical structure of the domain based on the goals. This is an example for the transportation domain. It doesn't matter what is here. What I want to just highlight is, you saw in the previous, earlier I showed a right recursive structure. So it really doesn't capture the domain. Look at how balanced this is, right? So this is a much more balanced hierarchical structure. So it's possible to learn that. Anyway, I'm getting to the end of my presentation. Let me talk about future work. I've been fascinated. I've been fascinated with this system developed by Josh Tannenbaum and his students. Kulkarni is the first author, called HDQN, Hierarchical DQN. And the way this works is a two-layer architecture. The meta layer will tell the, and I should say this is a hierarchical reinforcement learning algorithm. And it has, it's a deep learning algorithm, and it has two deep learning architectures connected into one, two CNNs. One is the meta controller and the other is the controller. The job of the meta controller is to generate the next goal. And the role of the controller is to achieve that goal. So the meta controller will produce a goal, and the controller will start planning, executing action, not planning, executing actions in the domain. It's reinforcement learning, so it's planning and acting in the environment at the same time. And there's this critic here. This critic is just checking whether the goal has been achieved or not. And now it will continue acting until it reaches the goal. When it reaches the goal, then it will go back to the meta controller and produces the next goal. Oops, so, oh, I had a figure and I missed it. That's fine. The figure was saying you start with a goal, perform some actions, actions. until you reach the first goal, and then this meta controller will produce the next goal and produce it again. The reason I'm mentioning that in this context is you could represent the sequence of goals as a right recursive hierarchical structure. I think there is an opportunity here to use these kind of multi-layer architectures to learn these hierarchical decompositions. And as you know, these reinforcement learning algorithms, they act on the environment. So they're learning this, in this case, the goal sequences and how to plan. They're learning the actions. I think there is an opportunity there to explore combining HTN planning with these kind of architectures to do something like hierarchical deep learning task network planning. So if you do that, I didn't coin it, you'd coin it if you work on that. That's a potential work. Another one is, I've been misleading you in this presentation. In the presentation, I show the methods that I have shown in this presentation are a task, a collection of preconditions, and a sequence of subtasks. That's what I've been presenting. But actually, that's not, HTN planning is much more powerful than that. If you look at the system SIPE, for example, or SIPE2 from David Wilkins, the subtask is not a sequence of tasks. When I have a method and I want to decompose it, they have a schema of how to decompose the method. So they will have some tasks in some conditions, and this is the actual decomposition of method, not a sequence. Some of you may recognize this is the Sussman anomaly, but the point here is these methods, of course, they are handcrafted. These methods are much more powerful than just sequence of tasks. They have a structure, conditions, ordered conditions, but here you have a join. You have to perform this task, and you can join it before you can perform this task. You have this order here so there are these much more powerful structures. So what I'm saying here is the problem of learning HTN methods, but now having these more complex decomposition schemas, that's pretty much open. I don't think anyone has worked on that. And they are powerful reasons. This book is called Practical Planning, based on actual applications of SIPE2, where you need these kind of much more powerful representations. Same for temporal conditions. Luis Castillo. Luis had an HTN planner system. It also is similar to this one in that it has these partial orderings, but it actually has timelines. You see these numbers here, 8 a.m., 2200, 8 a.m. next day, nighttime, daytime. It has a scheduling information, temporal information that is part of the plan representation, HTN plan representation. This is work is on HTN planning. So again, the problem of learning HTN representations that would include those temporal conditions is pretty much open. So I don't know if anyone who has worked on that. Something else that I want to, this is my last slide, but it just occurred to me when I was looking at preparing this presentation, nobody has written a paper or an article with an overview of HTN learning methods. And I'm ashamed to say I should have written it back years ago, but I have not. And now at NSF probably I will have less time to do that. You are starting, and if this is a topic that interests you, this will be a good way to start, is to write an overview article on what is out there on learning HTNs. And with that, I want to thank you for your attention. I'm happy to answer any questions you may have.
Oh, thank you very much, Hector. You've already got a question there from Salar.
Yes, Salar. I must say infrequent. So the question, let me read aloud. The question, how commonly are learned HTNs used in practice? Very infrequently. All of the words that I know of applied HTN system, they all have been handcrafted. I would go further, say that I do not know of works where the learned HTNs have been used in actual domains. I know in actual deployed application, I don't know of any. So the answer, none so far. Salar, maybe you will be the first.
Okay, there's another question from Daniel Wang.
Okay, how do you measure the quality of a learned HTN versus a handcrafted one? Good one, good one. We have done that. Okay, so this is a good question, right? So we give the procedure, we give the training data, the multiple traces, and we learn the domain, an HTN domain, but a domain expert could have crafted the HTN domain. So the question here from Daniel is how we will compare the two. And this has been done, and there are multiple metrics by which they compare. So comparing the HTNs that are learned automatically, the methods, versus those that are handcrafted. So I'm going to tell you a few that I have seen actually. So the ones that I'm going to mention are not imagined, they are written in papers. So the one on mentioned with MaxSat, they had the ground truth, right? They had the handcrafted methods. What they were comparing is they will go method by method and basically compute false positive, false negative. Meaning, if you have a precondition in the learn method that was not a precondition in the handcrafted method, then that's a false positive. A false, it's a false condition. I don't know which one was the negative. Or if you have a condition that is missing in the learn method, that is a condition in the one that is handcrafted, then that will basically count those number of errors. So one is by direct comparison between the learn methods and the crafted and the handcrafted method. So that's one possibility. Now, for some other works, it's not possible to do that comparison because when you're learning the structure, that means you're learning the method yourself, so you cannot make a one-to-one comparison. Then in those cases, there are two metrics that I have seen perform. One is the obvious one. Let's use the handcrafted one and let's use the learned ones, plan with those, and let's see, how many plans were correctly generated. What is the time that it took to generate those plans, and what is the length of the plans generated? Obvious one. The final one that I have seen comparing both is a metric of the complexity by simply counting how many methods were learned in the automated versus how many were handcrafted. And then you count how many preconditions do you have on average in a handcrafted method versus how many in a learn method. And if I may say, for earlier systems, it was dismal. And by dismal, I mean is the handcrafted transportation domain. If we use CHOP, this HTN planner CHOP, and I don't allow the if then else. So every composition is its own method. You and I could write with 6 or 7 methods. We could represent the whole transportation domain. And the learn system would require 30 or 40 methods. So it was several orders of magnitude larger. More recent methods, procedures are faring better, but this one sticks in my mind of something that was a big difference. So next question is it from Simona? Is it possible to have a different sequence of actions that compose the same method? Yes, yes. And in the example that you have there, Simona, it will be an example. I have lunch where I will eat and drink something, and I have other lunch where I eat something else and doesn't drink anything. In fact, in the example that I was mentioning with the getting from Lehigh to NSF, there would be at least 3 methods, right? I could, for the same task, I could basically drive directly from Lehigh to NSF, 3.5 drive, or I can drive to the airport and take an airplane and then drive from the airport in Washington, D.C. to NSF. Or I could drive to the train station, and this is literally, I could do that, and I have done all 3 of them, in fact. I could drive to the train station in Philadelphia, take the Philadelphia train, and go to Washington. So yes, Simone, is it possible to have different sequence of actions decomposing? Let me just clarify. I will not say the same method, but the same task. So you may have, for the same task, multiple methods, one for every sequence. Or for, I will not say sequence because every method will have a task decomposition and it will be continually hierarchical, but 3 different strategies to decompose the same task. Yes. If so, is it possible to apply machine learning to understand? Yes, so here is, let me finish the question. So she's asking, is there possible to apply machine learning to understand which decomposition is more efficient? Yes. So for example, this is work with Recruiter that we have done in the past. We assign a reward based on how many actions were generated in the decomposition. And we basically apply a very simple reinforcement learning schema that was trying to minimize the number of actions that was generated. It would prefer methods that will result in fewer actions being generated. So every method had a weight associated with it, and the weight was higher, the fewer actions were resulting from applying that method. And then we modify the chop planner so it will prefer the method that have higher weight that will result in fewer actions. Yes, that's possible. And this is the beginning, right? There could be more sophisticated. We use a very simple reinforcement learning algorithm. One could use others. Let me go back to the question. Okay. The next one is Benjamin is asking, is there a work on multi-agent HTNs? Oh, excellent question. So we have, let me think the answer to that. The answer is probably no. And this is a good question. We have done work on learning operators, not methods, but learning operators with multiple domains. I'm going to extrapolate for that. So the answer, Benjamin, is no. And let me just show you where it could be used. So you may have, for example, in the transportation domain, what happens if the truck is its own agent, and the machine, the crane that loads and unloads things are its own agent. In that case, you would like to learn strategies for the crane separately from the strategies from the transportation, but you also like to be able to work together. So yeah, Benjamin, work on that. Nobody has done, as far as I know, nobody has worked on that problem. Multiple learning HTNs for multi-agent HTN. I don't know of any work. Oscar is asking the question, are there HTN models encoded explicitly in description logics? Oh, I love that question. So there has been some work on integrating semantic web with HTN planning to do service composition. So Oscar, Google semantic web HTN planner, and I escaped the name of the fellow who worked on that. And what he was doing is he was doing the problem of, I'm going to do web service composition. And he modeled that problem as an HTN planning problem and work on that. So good. You can look at that. I don't think that people have looked at that recently. I will say that work, and I studied that. I am not co-author of that work, but it uses a subset of the semantic web representation. So maybe if you're interested in the topic, you can look into how you can expand on that. Simona is asking, also, does the context decide which decomposition is more efficient? Oh, okay. Yeah, Simona, work on that, because I don't know of any word. When the word that I seen that we work on that, it associated a weight to every method, but it was, obviously the methods have the applicability conditions, but there was no additional context that will compare, if you say like this, use method 1 instead of method 2, like that kind of selection, that was not working. I don't know of anybody who has done that. So what you're saying there, for example, I'm reading your text, depending upon what happened next, you would prefer to choose a composition over the other one? Yes, that's a good idea, and I don't know of anyone who has worked on that. Let me see if there are others. Any other questions?
Okay. So if there's no more questions, that's pretty good timing.
Very good. Thank you. That was wonderful questions, wonderful interaction. I think this will be stored somewhere, and you can realize there at the end of the presentation, I have some references, so you can look at them. But again, it's just what came to mind. I didn't do an exhaustive search for things. The paper, it would be great if somebody works on a paper on overview of HTN learning methods. Thank you very much. Thank you all.